So in this problem, this circuit is given and it wants us to determine the load, the impedance, the load, such that we have the maximum average power delivery to the load. Okay, so from the basically lecture notes, we know that in order to have a maximum power delivery to a load, Z of load needs to be Z of Thevenin conjugate. Okay, so therefore we have to find the Z Thevenin in part A, and then in part B also we want to find what's the now this maximum power. For that, as you see in the formula, we have V Thevenin. So therefore, we need to find both Z Thevenin and V Thevenin. In other words, we need to find the Thevenin equivalent seen from terminal A and B. Okay, so let's start with finding Z Thevenin. Okay, to do that, we can basically the first thing that we need to do is to zero the independent sources. So zero independent source. And then because we have a dependent source, we can put VS test source, and then we look at VS or IS. Okay. But also because our circuit, we are looking at a steady state, sinusoidal steady state, we need to also first find the impedances for our circuit elements. So let's look at L. So the impedance of L is ZL is J omega L. And omega is coming from the source. Omega is 10. So J times 10 times L, which is 0.1. This is J, this is Z of L. Z of C is minus J divided by omega times C. Negative J omega 10. C is 0.2 farad, which is negative J over 2 ohm. Also for later use, all IS also here, the source, phasor for the source is 4, it's cosine, so the angle is okay, so this is also our source. Okay, very good. So let's remove the IS, and I put the source voltage, test voltage VS divided by IS, okay? So this negative J over 2, and there is R, which is 3 ohm. There is L, which is J. So Vx, 10 source, Vx is here. I put the test voltage Vs. This is IS. And so there are different methods to solve this, basically. And remember, eventually we want basically Z Thevenin is VS over X, right? So I want a ratio of VS over X. So I will solve these two ways for you just as a practice. We can do node analysis or mesh analysis. So let's start with the node analysis. Node voltage analysis, right? So for node voltage analysis, As you know, we can look at the essential nodes and, like, for example, I go on this and I call this V1. And I will write KCL, right? Like KCL on the essential nodes. So, okay, so let's look at here. So the current, which is from V1 going up, that is negative IS. Then we have this current 2 times V of X. And then the current which is going to that loop is V1 divided by 3 plus J. So that's the KCL at this point. Now look at V of X. What is V of X? V of X is the current across the capacitor, which is basically minus J over 2 times the current that is going through that, which is IS. So therefore, I can replace Vx with this. But then also V1, I need to somehow write V1 also in terms of Vs and Is. And by look at here, actually, V of X is also Vs minus V1, right? So also we can say V of X is Vs minus V1. And in other words, V1 is Vs minus V of X, and V of X is this. Minus J over 2 minus. So it is Vs plus J over 2s. Very good. So as you see, therefore, in the equation 1, if you look at equation 1, I have found Vx in terms of Is, and also V1 in terms of Vs and Is. Therefore, if I replace these two in this equation, everything would be in terms of Vs and Is. So therefore, let's here, so negative Is plus 2Vx. 2 times Vx is minus JIS plus V1 divided by 3 plus J. Then V1 is V of S plus J over 2 IS, that is equal to 0. Okay, very good. So let me bring these to the other side. 1 plus J IS equals to Vs plus J over 2 IS divided by 3 plus J. Multiply this 2. 1 plus J plus 3 plus J times IS plus Vs plus J over 2 IS. So as you see, after this, we have this equation is just manipulating the equation. Just multiply this 3 plus J plus 3J plus J squared, which is -1. And let me also bring, this is times IS, right? And this is also IS. Let me bring it to the other side. Minus J over 2 IS equal to Vs. Very good. So 3 minus 1 is 2. And then 3 plus 1, 4 minus half J. 4 minus half is 2.5 J. IS equal to Vs. So Vs over Is, therefore, is this. So Z Thevenin is Vs over Is, which is 2 plus 3.5 J. This is Z Thevenin. However, you're not done, right? We need Z node, which is Z Thevenin conjugate. So conjugate of that is 2 minus 3.5. So our Z load is basically a resistor. This is our Thevenin, 2 and this other term is negative, J has negative J, so it means that there is a capacitor, which we can also find it C, easily can find it C, given that basically you have the omega. Also, just as a side thing. So this part is basically, or yeah, minus J over omega C is minus 3.5 J, right? So this part is 3.5, 1 over omega C is 3.5, and you have the omega from the top, omega was 10. Then you can find C. This is fine. Okay. But so far the problem didn't ask us, but just like a side thing. So this is more Z Thevenin. This method, again, that was a nodal analysis. I can also solve Z Thevenin, and again, practice using mesh analysis. Okay, so for mesh, we, as you know, we define the currents for each mesh. So let's call this I1. And this one. IS is going this way, I1 is, or this current is going the other side. So instead of defining a new current, I just put negative IS. I1 and negative IS. And we write KVL. So this is mesh analysis. So for mesh current analysis. Okay, so I wanted to write the KVL on this mesh, but I am hitting a current source, and that's basically a super mesh. So instead of going through this loop, I will just go around it. So basically the loop that I'm going to consider is this super mesh. Yeah, because there was a current source here and I was looking at the voltage. So I want to avoid this. So I go just around it. Okay, so let's like write the, starting from here, let's write the KVL, and this is 3 plus J times the current I1. I'm going this way, so I1 is also going that way. J plus 3 times I1. And then I'm going up. The impedance is negative J over 2 times the current, which is this way, which is negative IS. Right? And then plus V of S equal to 0. That is the super mesh, but also where is it? I have this current source, so I write the equation on the current source here. So 2Vx is I1 minus the current which is going up. Like this. Okay, so that's another equation. But also, what is V of X? V of X was the voltage across the capacitor is negative J over 2 times IS. Okay, so if I just put everything together, so this is our main equation, right? It has Vs, it has Is, so I have to get rid of I1. But what is I1? I1 has Is, which is good, but also has 2Vfx, and V of X is this. Okay, so basically we go step by step. Instead of V of X, we put here. So you get two times that. So putting this together, you get 2 times V of X minus J over 2 is is equal to I1 plus is. So basically I1 therefore would be minus is minus JIS. So minus 1 plus JIS. Good, and then I put I1. So therefore 3 plus J times I1, which is 1 plus J plus negative is. Minus and minus plus J over 2 is. Plus EFS equal to 0. I have to find a ratio yes or is, right? So let's put this the other side, or another way, EFS is equal to 1 plus J, 3 plus J is minus J over 2 is, which is exact similar equation as we had with the other analysis that we had. If I find it similar to this, so I get 2 plus 3 plus. Square minus 3 plus 3.5J, which is the Thevenin. But remember again, the load is the Thevenin conjugate, which is 2 minus 3.5J. And from that, this is 1. Okay, so this is the mesh analysis. As you see, we got the same. Okay, so the next step is to find the V-Thevenin. Finding V-Thevenin. And remember, this was the original circuit. For V-Thevenin, I have to basically find the V of open circuit. So I have to open the terminal A and B. And I call this plus minus V-Thevenin, which is the same as the open circuit. We need to find the V-Thevenin in this case. Let me do a mesh here, because I see some current sources, so probably the mesh would be a viable approach. So this is 4. I got this from the IS equal to 4 cosine of 10t. So magnitude was 4 angle 0. So this is 4, I put 4 here. And on this, also I can put 2dx. And remember, the current here is 0, right? This is 0. So the 4 is gonna go through. So this current is 0 because this is open. So we have 4 here. We have 2vx there. And let's do mesh. So as before, because of this current source, there's a super mesh. So I will consider this super mesh here. This here, there is a voltage, right? So I can write the KVL here. Let's start from here. Negative VTH. This is basically we have to find the voltage, right? So from here to here, there's like I hit negative, so negative VTH, and then I come here, negative J over 2 times the current. It's current which is going down. It's 4, and then I come here 3 times this current, which is 4 minus 2x. 4 minus 2x plus from here J times the curve which is going down. 2x is going up, so negative 2x is going down. This is equal to 0. Okay, very good. So everything is like good except v of x. I need to get the v of x, but v of x was here, right? So v of x is negative j over 2 times the 4, right? So negative 2j. So I just replace this here and so negative v to h minus 2j plus 12 negative 6 times v of x, which is negative 2j minus 2j times v of x, which is again minus 2j equal to 0. Okay, so let's do some math here. This is 12j. This is minus and minus plus 2 times 2, 4, j squared, which is negative 1. Which is 12 and so b Thevenin, to put b Thevenin on the other side, is equal to 12 minus 4, 8. And then 12j minus 2j is 10. This is in a Cartesian format, but I need to know the magnitude of the object. For the formula for the power max, remember the power average max is v Thevenin squared magnitude of that divided by 4 r Thevenin, but here remember if this is RMS. This is RMS, and if it's maximum, v Thevenin max squared divided by 8 r Thevenin. So in this case, if I find the magnitude here, which is a square root of 8 squared plus 10 squared, square root of 164, that's the maximum. This is the maximum, so I can use this formula. Or you can so P average max is this squared, which is 164 divided by 8 times r Thevenin, and r Thevenin was, I guess, 2 times 2. This is what in terms of what? Yeah. Then again, going back to here, as you see, the I was given in terms of the maximum. 4 is the maximum. There was no RMS at all, right? So because that I started with that, so everything would be in terms of maximum. That's why here that is the maximum. This is the Thevenin itself, and then I will use this formula. If you wanted to use that one, you have to find v Thevenin RMS. That's just for your information. As you know, the RMS is the max divided by square root 2. Then if you had this, we could use that. So this is 164 divided by square root 2. This is how much volts in terms of RMS. Then you could use this if you have RMS. Otherwise, you use the other. Okay.